Hello and welcome everyone to our weekly session titled Latest in Bitcoin Tech, where we discuss the Bitcoin Optech newsletter. And this week we will be discussing newsletter number 308, which was published on June 21st, 2024. Just an overview for those who've joined us for the first time, that Bitcoin Optech newsletter is a weekly tech-based newsletter that is published that contains the latest happenings in the tech world of Bitcoin. It covers developments in client software. It covers releases and release candidates, notable code clubs, summaries of peer review clubs. It also contains old versions of LND and summarizes continued discussion about PSBTs for silent payments. Also included are our regular sections describing recent changes to services and client software, announcing new releases and release candidates, and summarizing notable changes to popular Bitcoin infrastructure software. So we'll start with the news section, and we will first discuss the first news article. It's titled Disclosure of Vulnerability Affecting Old Versions of LND. Matt Morehouse posted to Delving Bitcoin the disclosure of a vulnerability affecting versions of LND before 0.17.0. LN relays payment instructions in Onion messages using Onion encrypted packets that contain multiple encrypted payloads. Each payload is prefixed by its length, which since 2019 has been allowed to be any size up to 1,300 bytes for payments. Onion messages, which were introduced later, may be up to 32,768 bytes. However, the payload size prefix uses a data type that allows indicating a size up to 2 to the power 64 bytes. LND accepted a payload LND accepted a payload's indicated size up to 4 gigabytes and would allocate that amount of memory before further processing the payload. This is enough to exhaust the memory and some LND nodes, resulting in them crashing or being terminated by the operating system. And it could be used to crash nodes that have more memory by sending multiple Onion packets constructed this way. A crashed LN node cannot send time-sensitive transactions that may be necessary to protect its funds, potentially leading to funds being stolen. The vulnerability was fixed by reducing the maximum memory allocation to 65,536 bytes. Anyone operating an LND node should upgrade to version 0.17 or 0.17.0 or above, upgrading to the latest version 0.18.0 at the time of writing is always recommended. Since we have some people here who are pretty new to Bitcoin, I will just first start by giving a brief overview of what the Lightning Network is, because this news article talks about or deals with a vulnerability that was detected in LND, which is an implementation of the Lightning Network. Okay, so until and unless we don't know what a Lightning Network is, we will not be able to comprehend this news article. What is the Lightning Network? It's basically an L2. It's basically an L2 for the Bitcoin mainnet. All right. So we all know what the Bitcoin mainnet is. I'm assuming all of us might have used it or learned about it. There are certain limitations of the Bitcoin mainnet. Okay. One of them is that it's not very cost incentive. It's not really intensive. Sorry, it's not very cost intensive to make small payments on Bitcoin's mainnet because of the fee being very high. Okay, and also the settlement time is pretty high. Generally takes 10 minutes for one block to get mined. So if one person is sending a transaction to another person, it on an average takes 10 minutes for that transaction to get confirmed and get included in the block. Okay. So we need a solution. We need a solution to make Bitcoin a medium of exchange, right? Because if you're buying a coffee, then you are not willing to pay 30 or 40 US dollars as a fee for paying for that cup of coffee. Nor are you willing to wait for 10 minutes to settle the transaction at the coffee store, right? So there are a lot of scaling solutions which are known as layer 2 solutions that are being worked upon, okay, that can allow quicker settlement of Bitcoin transactions at a very low cost. One of them, and the most popular of them, is known as the Lightning Network, right? You'll find a lot of articles and podcasts and internet material to familiarize yourself with what the Lightning Network is. The overview is that it's a layer 2 solution which enables Bitcoin to scale, which enables people to make minuscule day-to-day Bitcoin payments with very low cost of making those payments, which is not possible on the mainnet. All right. So that's what the Lightning Network is. It is one of the various scaling solutions, layer 2 solutions for Bitcoin. And the most popular one today is the Lightning Network. LND is one of the most popular implementations of the Lightning Network. So this news article talks about a vulnerability that was detected in a certain version or certain versions of LND, which is an implementation of the Lightning Network. Okay. So this vulnerability was affecting the versions of LND before 0.17.0. Okay, the vulnerability has now been mitigated. It affected the versions below this. So if anybody is running an LND node, okay, which is of version below this, then as per this article, the author recommends you to upgrade to at least this version to circumvent this vulnerability. Now, what is this vulnerability? First, we'll talk about it on a surface level, and then we'll probably try and dig into more detail if we can. So the vulnerability is such that on the Lightning Network, basically you use something known as an onion message. Okay, something known as an onion message. What's an onion message? Okay, let's first look at what is an onion message. Okay, just like on the Bitcoin network, there are peers, right? And the peers gossip with each other, they share information with each other. On the Lightning network also we have peers, right? Just like we have Bitcoin nodes, we also have Lightning nodes that gossip with each other, that share information with each other. And how is this information shared? It is shared in the form of onion messages. Okay, so this might not be, wait, I think there's a nice article on Wikipedia about onion messages. Yeah, so we just read some lines of this to understand what onion messages are and what onion routing is and how information is shared among peers on the Lightning Network. So onion onion routing is a technique for anonymous communication over a computer network. Okay, in our case, it's the Lightning Network. In an onion network, messages are encapsulated in layers of encryption analogous to the layers of an onion. So it's called as onion routing because there are multiple layers to this message. Okay, so basically this message can have multiple layers. Okay, so for instance, there's an Alice and there's a Bob. All right, and Alice wants to send a lightning payment to Bob, but Alice does not have a direct lightning channel open with Bob. Okay, but Alice has a channel with Charlie, Charlie has a channel with Dan, and Dan has a channel with Bob. So Alice does not have a direct channel with Bob, so Alice will now route her payment through Charlie and Dan and Bob. So Alice will send the payment to Charlie, Charlie will forward it to Dan, Dan will forward it to Bob. Okay, so that's known as hopping, and that is why we use onion messages. Why? Because as you've all of us have seen what an onion looks like, right? You peel the onion, the onion has various layers, you peel the layers of onion, right? So because the message is not only intended for one person, right? The message first needs to go to Charlie, Charlie will then send the message to Dan, and Dan will then send the message to Bob. Okay, and it is important that every participant in this routing only gets access to information that is specific to him, right? So Charlie only needs to get information that is specific to him. Dan only needs to get access to information that is specific to him. And Bob only needs to get information that is specific to him. All right. So how do we ensure this? We ensure this using onion messages. Okay. So these onion messages are messages that have multiple layers to them. So when Alice routes this onion message or this piece of information to Charlie, who is the first participant in this route, Charlie will peel the first layer and gain access to information that is only specific to him. Okay, and then he'll forward it to the next participant. The next participant will peel the next layer and get the information that is only specific to him, and then he'll forward to the final participant, who will, in our case, peel the layer and find the message, which is the lightning payment. So this is how it works like, all right? So for example, assume this is an onion message. Okay, so there's the first layer. Okay, so the first participant in onion routing will get the message. Okay, it'll peel the blue layer. Okay, and then it'll forward it to the second participant, it'll peel the green layer, then to the third participant, they'll peel the orange layer, and then to the final participant who will get the message that is a lightning payment. So this is like the analogy that is common between how information is passed between participants on the lightning network and how an onion's layers are peeled, and that is why these messages are known as onion messages. So coming back to that, all right. So what happens is these, okay, what now we know what onion messages are. Okay, so now there's this another terminology known as payload. Payload is that piece of information that every participant in the route needs to have access to. So, okay, so when you send an onion message, it has a specific payload for the first participant, which has all the information that that participant needs to know to further route the payment. Okay, and then it goes to the second participant, and there's a payload that is specific to that second participant. When that second participant will peel its onion layer, it will get access to that payload which is specific to it, which has all the information that the second participant needs to know. Okay, so now we know, as an overview of what the Lightning Network is, what onion messages are, what payloads are. Okay. Now this payload is, it contains of a prefix of the length, okay, of the length or the size that it contains, and it's very common even in Bitcoin that way when you share a piece of information, you precede it with the amount of memory that is required to store that piece of information. In fact, this is very common throughout computer programming, right? Even when you declare a variable and you don't initialize it, right? Let's assume a basic Python program that you're writing. Even if you're writing your first hello world program, right, what do? You first, for instance, go and write int a, okay, and then a is just a variable. Okay, it's just a variable, you've not even initialized it. What does the compiler do? The compiler sees that you want to create a variable by the name of a, which is of type integer. So the compiler will allocate certain space for that variable a. Okay, how much is that space? That space will be adequate for you to store an integer. So when you don't initialize a variable in computer programming, you just declare it. The compiler allocates that amount of memory which is required to store that variable. Okay. So in Bitcoin also, it is very common that when the participants need to share, when the participants of the peer-to-peer network need to share information with each other, they will very often precede that information with the size of that information or the length of that information, which gives the node an indication of how much amount of memory the node needs to allocate in order to pass and store that information. Okay, so even in the Lightning Network, this is what happens when you are passing on an onion message. Okay, and when the onion message reaches a certain participant in the routing network, the participant will get access to its payload. Okay, that payload has all the information that the participant needs to know to further forward this message. Okay, now before the participant accesses this payload or tries to pass it, this payload is prepended with a prefix. Okay, that prefix tells the node that, hey, you need x amount of memory, you need to allocate x amount of memory to store this payload. Okay, that is what this prefix is talking about. All right, now where does the vulnerability come into picture? Okay, we'll read this article to understand what the vulnerability is. So far, I hope that everybody understands what the Lightning Network is, what Lightning nodes are, how information is shared in the form of onion messages over the Lightning Network, what a payload is, okay, and what a prefix for that payload is. All right, at least these things I hope that everybody was able to comprehend. If anybody has any questions, anything to share, please go ahead and do so before we move forward. Cool. If none, let's go to the article. So the article is also very short. Okay. There's another blog post which is more interesting and more detailed. We'll go through that blog post as well. Okay, so this is Delving Bitcoin. Basically, this is a platform where a lot of Bitcoin and Lightning developers come and share information. So if you're new to Bitcoin, if you want to catch up with what's happening in the world of Bitcoin, this is a place where you'll find a lot of reputed Bitcoin developers and a lot of reputed Lightning developers coming up and sharing their ideas and discussing things. So you'll find a lot of Bitcoin core contributors. You'll find a lot of LND contributors, a lot of LDK contributors. You'll find them there. Like, this is the place where they hang out, Delving Bitcoin. Okay, and most of the news articles that we cover in the Optech newsletter generally are picked up from this place. All right. So Matt Morehouse, who is the one that came up with this proposal based on which we're discussing this news article, we'll just go through what he posted. LND versions prior to 0.17.0 are vulnerable to a DOS attack where malicious onion packets cause the node to instantly run out of memory and crash. This OOM is out of memory. If you are running an LND release older than this, your funds are at risk. Update to at least 0.17.0 to protect your node. All right. So what the vulnerability is, when decoding onion payloads, LND did not do proper bounds checking on the decoded length of the payload. The sender of the onion payload could set a length of up to 4 GB, and LND would allocate that much memory to decode the rest of the payload. By sending multiple malicious onion payloads, An attacker could cause LND nodes to OOM, okay, which is out of memory, crash within seconds. Due to onion routing, the source of the attack would be trivially concealed. Protecting your node, how do you protect yourself from this attack? Update to at least LND 0.17.0, which had did a bounce check on onion payload lengths. Okay. So if anybody is running a lightning node of this specific implementation, LND, okay, then they are recommended by Matt Morehouse to upgrade to a version which is at least 0.17.0. Okay, now what the vulnerability is, all right, just now I discussed, like for instance, when you are declaring an integer in a computer program, you say int a, which gives a hint to your compiler that you want to use a variable by the name of a, and the compiler needs to allocate memory which is adequate enough to store an integer. So here also the same thing happens. Okay, when you're sharing a payload with any participant in the Lightning Network, you need to indicate them how much memory should their node allocate to pass and store the information which is stored in that payload. What was happening is that in the versions of LND prior to 0.17.0, it was possible for somebody to put a value uh, of the length up to 4 GB. Okay, up to 4 GB. So the node would allocate 4 GB. Okay, so you're sharing a payload. Okay, you're sharing a payload, and the payload cannot exceed 1300 bytes. That's like the standard length of a payload. A payload cannot exceed more than that. Okay, but there is a prefix, like I said, right before the before the payload. There's a prefix where you indicate how much amount of space should the node allocate to pass and store that payload. It was possible for somebody to put a fake value over there, a false value over there, as long as 4 GB. Okay, so even though your payload is very small in size, it was possible for an attacker to put a prefix of up to 4 GB, which would tell your node that, hey, you need to allocate 4 GB to pass this payload, even though the payload needs nowhere close to 4 GB. It needs less than 64 KB, but an attacker could put a fake value. Okay, could put a fake value to deceive a node, and the node would end up allocating 4 GB. Okay, which obviously, if your node does not have space up to 4 GB, the node will crash. And even if the node has space up to 4 GB or 10 GB or 20 GB, it's very easy for an attacker to send 4 messages or 5 messages. Okay, and then eventually 4 GB you allocate for one message, one payload, 4 GB for another payload, 4 GB for another payload. Eventually your node will crash. Okay, and what are the repercussions of the node crashing? We'll try and discuss that at the end as well, because the repercussions and the ramifications of a lightning node crashing are much higher than a Bitcoin node crashing. Okay, so the point being, what's the vulnerability? That while indicating the amount of data that your node needs to allocate in order to pass that payload, an attacker can put a fake value which can go up to 4 GB, deceiving your node, and your node will end up allocating or try to allocate 4 GB of memory. If your node does not have 4 GB of memory, your node will crash. Even if your node has 4 GB of memory, it's possible for an attacker to send multiple such messages and eventually crash your node. Okay. We'll read through a blog post, which is also not very big, which is also authored by Matt Morehouse. All right. He calls this attack an LND Onion Bomb attack. Okay. What is this? LND versions prior to 0.17.0 are vulnerable to a DOS attack where malicious onion packets cause the node to instantly run out of memory and crash. If you are running an LND release older than this, your funds are at risk. Update to at least 0.17.0 to protect your node. Okay, what's the severity of this attack? It is critical that users update to at least LND 0.17.0 for several reasons. Okay, so the author now enlists a few reasons which will trigger or intrigue or maybe even force the users to upgrade. What are those reasons? The attack is cheap and easy to carry out and will keep the victim offline for as long as it lasts. All right. So this attack is very cheap. You don't need to spend a lot of money, right? So for instance, if somebody wants to pull off a 51% attack on the Bitcoin network, right, they will have to spend an exponential amount of money, right? But this attack is very cheap. Like you just have to send one message with a payload and put a fake value of the length of that payload in the prefix, and that's it. You can easily crash the node. So it's a very cheap attack to perform. All right, and that is why attacks that are very cheap and easy to pull off generally have a very high severity. Okay. What's interesting is that it says that it will keep the victim offline for as long as it lasts. Okay. Now, what happens in the Bitcoin network is that even if your node is offline, right? Even if your node is offline, if you're running a Bitcoin node, even if your node is offline, if somebody sends you a payment, you will still have access to that payment, right? That payment will still belong to you, right? Because there are other nodes who will relay that payment, okay, and then that payment will go into the miner's mempool, and the miner will mine it, and then the payment will go into the blockchain, all right? And whenever you come online, you will have access to that uh, uh, you will have access to that payment, okay? But the lightning nodes don't work that way, all right? The lightning nodes don't work that way. The lightning nodes have to be online all the time, right? Because your lightning channel is specific to your lightning node. Your lightning channel and your lightning payments can only be routed as long as your node is online, all right? So you have to be constantly online to receive payments, and your node has to constantly watch out for something which is known as a revoked commitment transaction. Like if any of you have gone through the mastering the Lightning network, or any of you are already familiar with how the Lightning network functions on a high level, then you all know what is a revoked commitment transaction. Okay, so the transaction with which you start a Lightning channel is known as a funding transaction, and the transaction with which you end the Lightning channel and go to the mainnet is known as a commitment transaction. Okay, so the commitment transactions could be of two types. Okay, one is which is a mutual commitment transaction which is signed by both the participants mutually, meaning both the participants in the Lightning channel agree to go on the mainnet. The second is known as forced close, right? Where one person wants to close the channel and the other does not want to close for some reason. Okay, now this is where this revoked commitment transaction can come into place, all right? Because every time you make a payment on the Lightning network, you update the status of the Lightning network, all right? The funds keep changing, they're not static. Okay, so it's possible that you are offline, all right? Somebody pulls off an attack on you, the onion bomb attack that we're talking about. Your node crashes because your node doesn't have 4 GB of data, let's say, and you're offline, and you have a Lightning channel opened with Alice exploits this situation, and Alice can broadcast a revoked commitment transaction, all right? Meaning Alice can broadcast an old state of your Lightning channel. Okay, so let's assume at the start you started a Lightning channel with Alice. Initially, Alice had 100 sats, you had zero, let's assume. Okay, then Alice gave you 20 sats, now it's 80-20. Then Alice gave you 20 sats more, now it's 60-40. Then Alice gives you 20 sats more, okay, now it's 40-60. Alice has 40, you have 60. Now your node crashes and goes offline, all right? Alice can take one of the old states, all right? Old state where she had 100 and you had 0, and she can broadcast that old state, all right? And if your node is online, your node can catch her and penalize her. But if your node is offline, your node cannot catch her, all right? And that old state will get redeemed. It'll be included in the block and it'll get mined if your node is offline, all right? So your channel partners can cheat you by furnishing an old state, an expired state of the Lightning channel, and thereby robbing you of your funds if your Lightning node is not online, all right? So it's very imperative and important that whoever's running a Lightning node and establishing a Lightning channel through that Lightning node, their Lightning node needs to be online all the time to catch anybody who's trying to cheat them and furnish a revoked commitment transaction. So this is another reason why this attack is so severe, because it's very easy and very cheap to perform, and your Lightning channel partners can rob you of all the sats that you owe them in the Lightning channel by furnishing an old, a revoked commitment transaction which has an old and a stagnant state of the channel. All right. The source of the attack is concealed via onion routing. The attacker does not need to connect directly to the victim. All right. So what happens in onion routing is that, like we discussed, that when you peel your layer of the onion, you only get information about your preceding node and your proceeding node. You only know that, okay, such and such node has sent me this onion message and I have to forward it to such and such node. You don't know anything other than that. All right. So if there are 10 nodes in this routing, all right, node 1 forwards the onion message to node 2, and 2 forwards it to 3, 3 forwards it to 4, 4 forwards it to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, and 9 to 10. 3 will only know 2 and 4. Okay, 3 will only know that I have received this message from 2 and I have to forward it to 4. 3 will not know anything else. All right. So the attacker is concealed. All right. So if the attacker is 1, 3 will not know who attacked them. All right. So if, this is another reason why this attack is so severe, because the source of attack might not be known to the person who's been subjected to the attacker. All right. Prior to LND 0.17.0, all nodes are vulnerable. The fix was not backported to the LND 0.16.x series or earlier. All right. So what's the vulnerability? Once again, the Lightning Network uses onion routing to provide senders and receivers of payments some degree of privacy. Each node along the payment route receives an onion packet from the previous node containing forwarding instructions for the next node on the route. The onion packet is encrypted by the initiator of the payment so that each node can only read its own forwarding instructions. All right. Once a node has peeled off its layer of encryption from the onion packet, it can extract its forwarding instructions according to the format specified in the LN protocol. All right. So this is how the code looked like. All right, prior to LND 0.17.0. So all the versions of LND, all right, which I repeat is an implementation of the Lightning Network. Uh, Previous to this specific version 0.17.0, this is how the code looked like. All right, the code that passed the payload, this is how it looked like. All right, so basically your payload size was uint 32. All right, so there was no checking being done. All right, there was no checking being done. So the person who's attacking could have put a prefix and which could go up to 4 GB. All right, if you see what is the maximum amount of data that can be stored in a variable of this data type, that's uint32. If you Google it, you see it's 4 GB. All right, so earlier what was happening was it was possible for somebody to put the prefix which indicated the amount of memory that needs to be allocated to pass the payload. It could be the maximum value could be 4 GB, all right, because there's no upper bound check being done. All right, so you can put a value of up to 4 GB, and if your node does not have 4 GB of space, it crashes. This is the old version of the code before 0.17.0. All right, and then this bug was fixed in the version 0.17.0 and above. How is it fixed? Now we do an upper bound check. Where is that upper bound check that we do? Yeah, here is the upper bound check that we do, all right? So we check the value of warrant, all right? If the value of warrant, meaning the value of the prefix that determines or that indicates the amount of memory that needs to be allocated to pass the payload, all right, we do an upper bound check. If it is greater than uint16, what is uint16? We check uint32 is 4 GB. Let's check what uint16 is, all right? It's 64 kbs, all right? 64 kb. So earlier we were allowing up to 4 GB, but now we are doing an upper bound check to ensure that the prefix that indicates the amount of memory that needs to be allocated for the payload is not above 64 bytes or 64 kb. Sorry, this is the upper bound check that we're doing, and if it's greater than 64 bytes, we just throw an error. Payload size of uh, is larger. Basically, we indicate that the payload size is larger. So this is the fix that we're doing. All right, just let's go through the DOS attack once. It is trivial for an attacker to craft an onion packet that contains an encoded length of uint32 max for the victim's forwarding instructions. If the victim's node has less than 4 GB of memory available, it will OOM crash instantly upon receiving the attacker's packet. However, if the victim's node has more than 4 GB of memory available, it is able to recover from the malicious packet. The victim's node will temporarily allocate 4 GB, but the Go garbage collector will quickly reclaim that memory after decoding fails. So nodes with more than 4 GB of RAM are safe, right? No, not quite. The attacker can send many malicious packets simultaneously if the victim processes enough malicious packets before the garbage collector kicks in, and OOM will still occur. And since LND decodes onion packets in parallel, it is not difficult for an attacker to beat the garbage collector. In my experiments, I was able to consistently crash nodes up with up to 128 GB of RAM in just a few seconds. That is like an unimaginable amount. I mean, like, I don't know how many people are using Lightning nodes that even have that much of RAM, 128 GB. All right, so this attack can even crash a node that has 128 GB of RAM space available. That has been tested by the author. All right, so yeah, this is what this news article broadly had to cover. It dealt with a vulnerability which was detected in LND. LND is one of the popular implementations of the Lightning Network. We discussed what the Lightning Network is. We discussed what LND is. We discussed what onion messages are. We discussed what payloads are. We discussed what prefixes are that determine the size of the payload. All right, and we discussed how an attacker can very cheaply exploit this vulnerability and crash nodes. And once your Lightning node is crashed, it goes offline. We also discussed how hazardous that could be, and how your Lightning channel partners could cheat you and exploit the fact that you're offline. All right. Let's just have a look at not actually, but an overview of how the onion messages look like. All right. So basically, if this is an onion message, okay, this is the overall structure of the packet, the onion packet. Okay. So it contains of what we're interested in is the payload. All right. It includes the payload. The payload contains the information. All right. So here we see the hop payload is a structure that holds obfuscated routing information and associated HMAC. It is 1300 bytes long and has the following structure. Okay. So the payload contains information. When you peel, when a router on the Lightning network peels its layer of the onion, quote unquote, it gets access to a payload. That payload gives it all the information that it needs to further route the onion message. Okay. Okay. This HMAC is basically, I think, it has to do with a shared secret, right? So you're like, when you receive the onion message, you need to be authorized to open or peel that onion message, right? You do that using a shared secret. Okay, that shared secret is deduced using the elliptic curve Diffie-Hellman, something called as the elliptic curve Diffie-Hellman key exchange. Okay, that is how you deduce the shared secret. So basically, all right, and now let's dig a little deeper into how the hop payload looks. All right, this is the hop payload. All right, this is the onion packet. One of its components is the hop payload. Now this is the hop payload, and what are the components of the hop payload? This, all right, this length. This is what we are talking about. This is what the entire article is about, right? You first stipulate what is the length of the payload. All right. So first the node will process this information length. Okay. And if the length is 4 GB, your node will try to allocate 4 GB to pass this payload. All right. And crash. But now what we're doing is, when the length is stipulated, we are ensuring by an upper bounds check that the length should not be more than 64 KB. If it's greater than 64 KB, we'll directly send an error. We'll not allocate any memory. If it's less than 64 KB, then yes, we'll allocate the memory, and then further we'll start passing the payload. All right. This is what this news article contained. And we've covered the first one. So any questions, any thoughts, any observations, anything anybody would like to share? I'll just drink water for 10-15 seconds. If anybody has anything to share or ask, please do so. All right. All right. No questions. We'll move forward.
Faisal, Coding P asked a question in the chat.
Oh, okay. Sorry for the digression, but what happens to funds if due to some network issue or power cut, LN node goes offline? So there are two situations. Okay. If your channel partners are not trying to cheat you, okay, then you will not end up losing your funds. Okay. The situation that I describe is when your channel partner wants to cheat you. Okay. If you're offline, there are mechanisms that your channel partner will send you a payment. All right. That payment will not reach you until and unless you come online. You come online and then the payment reaches you. Okay. This is when everybody plays honest and everything is hunky and dory. So when all your Lightning channel partners are honest, and if you go offline for some reason, nothing happens. You don't lose your funds. You come back, you sync with the channel graph. All right. Just like it happens with a Bitcoin node. When a Bitcoin node goes offline, for some time you come back online, your Bitcoin node syncs with the network, right? You go through something known as a block download, right? IBD, and then a Bitcoin node syncs with the network till it's in sync with the current status of the network. The same thing happens in the Lightning network. All right, there's this thing called as a channel graph. All right, the channel graph basically is a map of the entire Lightning network. It's the latest snapshot of the Lightning network. So when your Lightning node goes offline and when it comes back online, it syncs just like your Bitcoin node syncs. So it will sync with the latest channel graph. All right, and any payments that were sent to it, when it's online, it will receive those payments. All right, so if everybody is being honest, you don't lose any funds. All right, the catch is when any of your channel partners want to cheat you. All right, because in the Lightning network we have this thing known as the penalty mechanism. All right, where if one person tries to cheat, the other person catches them cheating. All right, there are two participants in a Lightning channel. If one participant tries to cheat, the other participant catches them cheating. All right, the cheater will be penalized. The cheater will lose all the funds. All right, so let's say there's a Lightning channel between person A and person B. All right, person A has 60 sats and person B has 40 sats. Okay, person A tries to cheat and person B catches them cheating, person B gets all the 100 sats. All right, that's how game theory works in the Lightning Network. So if you try to cheat, or if anybody tries to cheat, and their Lightning partner cheats them, catches them cheating, all right, the cheater gets penalized, and all the funds in the Lightning channel go to the person who has caught the cheater cheating. All right, but to catch your Lightning partner while they are cheating, you need to be online, right? If you're offline, your Lightning partner can cheat you, all right, and you're offline, you can't catch them, so they get away with cheating. All right, so there's a time span given to you, which is the time span of your HTLC within which you have to catch them. All right, so if a cheater cheats, you get a certain amount of time. Within that time frame, you have to catch the cheater to penalize them. All right, but if you're offline for that time span, you don't come back online for that time span, the cheater will cheat and get away. All right, so broadly, if everybody is being honest and nothing happens, you don't lose your funds, your node just comes back online and syncs with the latest snapshot of the Lightning channel graph. But if your channel partners try to cheat you and you're offline for a long period of time, then yes, you might end up losing all your funds. I hope I answered your question. You're welcome. All right. Yeah. So we will have to cherry pick and hop throughout the newsletter. We won't be able to go through the entire newsletter because it's quite an expansive one. We have already covered, like we've given 40 minutes. We have 20, 25 minutes more. So let's go to a Bitcoin Core PR. All right, let's take the first PR. Bitcoin Core PR number 29325. Okay, so there are some participants who don't have access to the mic for some reason. All right, and I will not be able to know if anybody has written anything in the chat. All right, so Mango or anybody, if you'll see somebody's asking any question in the chat, please notify me because I have only one screen, so I can't look at this call. So Bitcoin Core PR number 29325 begins storing transaction versions as unsigned integers. Since the original version of Bitcoin 0.1, they were stored as signed integers. The BIP68 soft fork began treating them as unsigned integers, but at least one Bitcoin reimplementation failed to reproduce this behavior, leading to a possible consensus failure. See newsletter number 286. By always storing and using transaction versions using unsigned integers, it is hoped that any future Bitcoin implementation based on reading Bitcoin Core's code will use the correct type. Basically, this is a PR that talks about fixing a bug or an issue that was concerned with transaction version numbers. You guys who have enrolled for mastering Bitcoin, or I believe also those who have studied other elementary level material on Bitcoin, will be aware and familiar with what a transaction version number is. So would anybody like to take a shot at what a transaction number is, transaction version number is, either through your mic or through the chat? What is a transaction version number? Try and guess it, even if it's wrong, no worries. Transaction version number.
I'll take a shot. So
Yep.
Bitcoin transaction versions signal to rest of the network which implementation of Bitcoin code they are running. So this could be a Bitcoin node that supports SegWit transactions, or I think now with Taproot, it could also signal a different version number to signal that they support Taproot transactions. Is that correct?
Yeah, that's correct. That is correct. Nodes, I believe that support Tagwit, SegWit. I'm saying Tagwit. SegWit also support Taproot. All right. So yeah, primarily that's exactly what you say. But I think it's version number 2. Nodes that have version 2 support SegWit and Taproot both. So for those of you not aware, Bitcoin transactions have version numbers. In fact, all Bitcoin transactions start, if you look at a hexadecimal format of a Bitcoin transaction, it commences with a transaction number. Okay, so those of you who are going to do mastering Bitcoin, or those who have already done mastering Bitcoin, I have never read Grokking Bitcoin. I don't know if this is included in Grokking Bitcoin, or if you persist with further study cohorts with Bitshala, then you'll come across LBTCL, where you actually create transactions, all right, and view transactions in a hexadecimal format. All right, so they commence with version numbers. Okay, we'll try and see if we can look at the version number. There's an entire chapter dedicated to it in mastering Bitcoin. So we can see, if we see, we'll understand better. Yeah, there's an entire chapter dedicated to the anatomy of transactions in mastering Bitcoin, where you will learn in detail how a transaction looks like. So this is how a transaction looks like. Okay, so if anybody of you all will also run in chapter 2 or 3, I believe, you all will run a node on reg test. Okay, so when you run a node on reg test, you can do this testing. All right. So this is the RPC command that you give, get raw transaction. Okay, this is the transaction ID. So you pass the transaction ID as the parameter to this RPC command, get raw transaction, which will get you the transaction in hexadecimal format. Okay, and the first 4 bytes of that hex output is your version number. All right, I believe it is this 1 byte, 2 byte, 3 byte. Okay, it starts. Okay, so this is your version number. All right, in little endian format. So this indicates version number 1. So different Bitcoin transactions can have different Bitcoin version numbers. Okay, 1, 2 were considered the standard. Okay, maybe even when you're studying mastering Bitcoin, you'll get to know that 1 and 2 are standard. But after the book was published, now even 3 is standard. I think last week or a few weeks ago, 1, 2, 3, they're all standard transactions. Anything above than that is considered non-standard. Okay. So yeah, this is the entire Bitcoin transaction. Contains the input, contains the output. Starts with the version number. So when you see this means it's version 1. All right. Different versions indicate different things. All right. Version 1 indicates that it's a legacy transaction, meaning it will not support SegWit payments. It will not support taproot payments. Okay. It'll not even support absolute and relative time locks. Okay, which you'll also study in mastering Bitcoin. Version 2 means it will support absolute time locks, it will support relative time locks, it will support SegWit transactions, it will support taproot transactions. Version 3 means it will support truck transactions, which are also known as V3 transactions. All right. So this indicates that what features are compatible with this specific transaction. That's what a transaction number is. So up till now, what was happening is that the transaction version number was being stored as an unsigned integer, meaning you could also put a negative value. You could also put a negative value. And what was being done is that you could put a negative value, but it would be typecasted. It would be typecasted for the implementation of BIP68. What is BIP68? BIP68 implements absolute and relative time locks, I believe. Yeah, it implements relative time locks. Okay, using sequence numbers. So what was being done is, because absolute and relative time locks, all right, what are time locks? Broadly, time locks is basically you lock your transaction to a certain block height, okay, or a certain Unix timestamp up till which your transaction cannot be redeemed. So if you want to send a transaction to a person, but you want to ensure that the person cannot spend the transaction for a certain amount of time, you lock that transaction either using a relative time lock or an absolute time lock, in the relative time lock or an absolute time lock. So the transaction gets locked till that time. Okay. So transactions that have a version number of 2, only those transactions have these features. All right. Like just now we saw, this was 1. So you cannot time lock this transaction because it has a version number 1. When the version number is 2, you can time lock those transactions. So what was happening is that while passing this version number, all right, you could provide a negative value as well. Okay. But when checking was being done whether you can apply time locks to it or no, at that time it was being typecasted to a signed integer, meaning at that time it was being converted to positive. So even if it's -1, it'll be converted to 1. Even if it's -2, it'll be converted to 2. All right. Now what is being done is that it has been turned into a signed integer, meaning only positive values will be accepted, negative values will not be accepted. Earlier, you could put a negative value for a version number, it would be typecasted. But now we're not typecasting it anymore. We are only allowing version numbers which are positive, so that we don't have to go through the burden of typecasting them. All right. And also because different implementations have different mechanisms, and how depending on which they pass the transaction versions. All right. One implementation, I believe BTCD, which is a Bitcoin implementation written in Go language, I believe, it also allows a negative version numbers, meaning it does not even cast them. So this would lead to a consensus failure, right? Because some nodes, some implementations would recognize that transaction as it is, and some implementations would not recognize that transaction as it is. They would typecast it, which could lead to a consensus failure. All right. So now what this PR suggests it, let's go through the PR quickly, is that we do not accept values of transaction version numbers in the form of signed integers. Rather, we accept them on unsigned integers. Rather, we accept them only in the form of signed integers. Right, let's just read through this. Given that the use of a transaction's end version is always, no, I don't think this is relevant. We'll go directly. So there are a few changes that have been made in this PR. One change is that version number was initially referred to as N version. All right. So if you go through the code, whenever you see N version, it means the version number of the transaction. Now instead of N version, we're using version, only version. Okay. Let's go through the comments. So yeah, I think this is Peter Woola who suggested that instead of using N version, let us use unsigned version. All right. And I think one of the commenters commented that we should only use version. Okay, so basically, those of you who are new or want to understand how Bitcoin core development happens or are interested in pursuing this path, this is where it all happens. All right, this is how Bitcoin core contributors communicate with each other. Right, so eventually this version was being selected, and now instead of N version, the transaction version numbers are will be written as version. Concept acknowledged. Right. So yeah, see, this is how the person who opened this PR acknowledge it. I've added a commit that renames n version to just version. Know that it is not a scripted difference since a bunch of different variables share the same name. All right. So it was suggested that instead of referring to the version numbers of transactions as n version, we should refer to them as just version. It was acknowledged and the change was implemented. And we see the change. I think more than 40 files were changed. So there were around 40 files that contained this variable n version, and now everywhere from n version is changed to version. As you can see, it was earlier n version, it's now version. N version version. N version version everywhere. Okay. And as you can see, earlier we were accepting values up to, no, not this one. Yeah, see, now we doing this check. All right, we're doing this check of the version. Mm. Right, nothing much to look in the code, it seems. Okay, so yeah, broadly that is what the change was, is that we are firstly we changed the n version to version. Secondly, now we are only accepting unsigned integers. We are only accepting signed integers, meaning only positive values as version numbers. All right, so that is broadly what this PR deals with. Cool. Any questions pertaining this specific PR, or can you move forward? If any questions, let me know. Something in the chat. Understood. Thanks. Our versions also used to signal support when a soft fork is being implemented. Uh, no, I think the miners do that. That is what the miners do. The miners set a certain flag, not these versions. I don't believe these versions. No. To the best of my knowledge, these are not the versions that you use to indicate supporting a certain soft fork. No, it's the miners that, like for instance, if a miner wants to support transactions, if a miner wants to mine transactions that are of version 2, then they indicate it by putting a flag when they are mining transactions or in the blocks. All right. I think Dhruvel is also asking a question. So I'll move on to the next PR, then I'll come back to your question, Dhruvel, by the time you can type it. All right. We're at 8:59. We'll just try and quickly cover as much as we can by 9:10 because we started 7 minutes late. Right. Eclair or Eclair. This is another implementation of the Lightning Network. All right. So Lightning Network has various implementations. Okay. One of them is LND that we talked about. There's LDK. This Eclair. All right. So this PR is specific to Eclair. Eclair defines a new type of encoded node ID to be assigned for mobile wallets in a blinded path. This allows a wallet provider to be notified that the next node is a mobile device, enabling them to account for mobile specific conditions. Okay. So basically, what this PR does is that in a blinded path, what's a blinded path? We don't have the time to delve into what a blinded path is, but broadly, what's a blinded path is that the recipient can keep itself anonymous, right? So if you want to receive a lightning payment from someone, but you want to remain anonymous from them, you don't want to share your node ID all right, your topology in the network with the sender of the payment, then you can use something known as blinded path. In a blinded path, what happens is that just now we talked that in the Lightning Network we route the payments, all right. If Alice wants to send a payment to Bob and they don't have a direct channel with each other, Alice can route that payment through multiple hops, all right, through Charlie, through Dan, and A, B, C, D, till it eventually reaches the final recipient. Okay, what blinded path is that you can, like, certain amount of the path, all right, certain hops of that path are known. Okay, and after that you can blind the other paths, right? So if I am the recipient, I don't want the sender to know my public key, my node id. What I can do is that, for instance, if there are 10 hops in the path, all right, I can blind the last 3 hops, for instance, all right. It is done using cryptography, ECDH, all right, elliptic curve Diffie-Hellman, that you can blind some hops. So the sender who's sending you the payment will not know your public key and your node ID. All right. And you will be blinded, and maybe your subsequent nodes will also be blinded. All right. So in a blinded path which is supported by Eclair, what can be done is that you encode the node ID. All right. This is the information that you share the node ID, encode the node ID, which indicates the participants in the channel that their next hop is a mobile wallet, all right, so that they can configure the payment in accordance with that, because mobile wallets have bandwidth restraints, etc., and also like they do not perform all the features that a full Lightning Network node performs. So to optimize the experience of the mobile wallets, what this PR aims to achieve is that it notifies if there is a mobile wallet in a blinded path, so that changes can be made in accordance to route the payment to a mobile wallet. All right, and the mobile wallet is not treated like the full node or the full archival node. All right, that's what the PR does. Just give me 1 minute. All right, I'll get back to you all. If Hey, sorry guys, my phone was ringing constantly. It was a very important. Sorry. Yeah, so yeah, this is the PR of Eclair. All right. The next PR is of LND. PR number 8730 introduces the RPC command LNCLI wallet estimate fee, which receives a confirmation target as input and returns a fee estimation for on-chain transactions in both SAT per kilowatt, that is Satoshis per kilowatt unit, and SATs per virtual bytes. All right. What this PR does is that just now we talked about that the transaction with which you start a Lightning channel is known as your funding transaction, and the transaction with which you close the funding channel, you close the Lightning channel and go on the main net, is your commitment transaction. Okay, so for your commitment transaction, you can put a target input, right? If you want your commitment transaction to get included in the next block, your target input is going to be 1. If you want your commitment transaction to get included in a block and mined within 2 blocks, then your target input is 2. If it's not urgent, if you can wait for 6 blocks, 10 blocks, all right, you can put that's your target input. So the number of blocks that you're willing to wait for your commitment transaction to get mined is your target input. If it's 1 block, it's 1. It's 2 blocks, it's 2. All right. So based on that, your fee estimation will give you an estimate of the fee, right? So this is an RPC command which you can trigger. You can pass an argument to it, which is the target as your input, and it'll give you a fee estimate. So if I want to close a Lightning channel and I want my commitment transaction to get included in a block immediately within 1 block, okay, then my target input is going to be 1, and I'll get a fee estimation that, hey, you'll have to pay X amount of fee if you want to get your commitment transaction confirmed within 1 block. If I'm willing to wait for 10 blocks, then my input will be 10. So I'll get an output saying that, hey, you'll have to pay X amount of fee to wait to get your transaction confirmed within 10 blocks. All right. So you can put a target input, the amount of blocks that you are willing to wait for your commitment transaction to get mined and included on the blockchain, and it'll give you a fee estimation in accordance with that. All right. So this is what this PR talks about. The next PR deals with LDK. I'm not sure if I should take this because this is going to be quite detailed. Still, we'll just read through it and I'll try and summarize it as succinctly as possible. LDK PR number 3098 updates LDK's Rapid Gossip Sync RGS to version 2, which extends version 1 by adding additional fields in the serialized structure. These new fields include a byte indicating the number of default node features, an array of node features, and supplemental feature or socket address information following each node public key. This update is distinct from the proposed Bolt 7 gossip update, similarly referred to as gossip V2. All right. So just now we discussed and coding P asked what happens if your Lightning node goes offline. All right. And I said that when your Lightning node goes offline and it comes back online, it syncs with the latest snapshot of the Lightning network. All right. There's this thing called Lightning Graph. All right. It has an information of all the public nodes and all the channels of that the public nodes are connected with. All right. So when your Lightning node comes back online, it is obviously not in sync with the latest state of the Lightning network, right? It needs to sync with the latest state of the Lightning network, all right? So it needs so it queries the channel graph basically, and the channel graph gives it the latest snapshot, and then the Lightning node like syncs to the current state. All right. Now this is a slightly time-consuming process. All right. So there is this thing known as rapid gossip protocol. All right. Now what this does is that this is this is a special provision you can say which enables mobile wallets. All right. When mobile wallets go offline and when they come back online, they do not have a lot of bandwidth and infrastructure to query all the nodes, because when you come back online you need to query multiple nodes, all right, to get the current snapshot or the latest state of the network. Even when your Bitcoin node goes offline, all right, there's no centralized server to which it can query, right? It generally queries its peers. It establishes connections with its peers, and then it queries its peers to get in sync with the blockchain. And your Lightning node does the same thing. It queries its peers and then gets in sync with the graph channel or the Lightning graph network. What RGS or our Rapid Gossip Sync does is that it is a semi-trusted server which your Lightning node can query to get the latest snapshot of the Lightning graph data. All right, so your node need not query its peers; it can just query a server that is running RGS, and that server will provide it the latest snapshot of the Lightning graph. Okay. And it also strips off some information, okay, because it is supposed to be very compact. It is supposed to be running on used by devices that run on limited resources. All right, so it strips off some information. All right, now the information that was being stripped off was not allowing the features like Bolt 12 offers, for instance, to get implemented, right? So now what is happening is that a new version of RGS is come, all right? So now when it shares information with the nodes that query it, all right, about the Lightning graph network, it shares specific information which allows more features like Lightning Bolt 12 invoices, etc., right? These new fields that it shares include a byte indicating number of default nodes, an array of node features, and a supplemented feature of socket address, all right? Because if you know what Bolt 12 is, all right, or what LN offers are on the Lightning network, to provide Bolt addresses of the recipient and the sender need to establish a direct connection with each other in certain situations. So you need to know the public ID or the socket address of the node to whom you are paying the money, all right? So which was not available using Rapid Gossip Sync because it was not sharing the socket address, but now it's been updated and now the socket address is also being shared, all right? This is what this PR talks about. Let's take one more and then we'll wind up the session. It's already 9:10. Which one should we take? Yeah, this is easy. LDK PR number 3103 begins using a performance scorer in benchmarks based on frequent probes of action payment paths. The hope is that this results in more realistic benchmarks, all right? So basically, when your node is trying to make a payment, your node is not, and it does not have a direct channel established with the person to whom you're trying to make a payment. You hop that payment, right? Like we've discussed throughout the course of this session, you hop that payment, all right? So this process is known as pathfinding, right? You find the path. So if Alice wants to send a payment to Bob and Alice does not have a channel with Bob, Alice will find a path, all right? Alice will find that, okay, I can send this payment to Charlie, Charlie can send it to Dan, and Dan can send it to Bob, all right? This is known as pathfinding. Now, what if there are multiple routes that take Alice to Bob, right? Alice can give it to Charlie, Charlie to Dan, and Dan to Bob, or Alice can give it to Matthew, Matthew to Luke, Luke to Bob, right? And this is a dilemma that all of us come across, right? If you want to go from destination A to destination B and there are two paths available, right? We see this very frequently in Google Maps, that Google Map will show that there are two paths available, but generally Google Map will suggest you to go through the more optimal path. So even in the Lightning Network, this happens that when you want to route a transaction, maybe there are two paths available through which you can route that transaction, maybe three, maybe four, maybe 10. All right. So the Lightning Network will always choose, or your Lightning Network implementation will always choose the most optimal path. All right. Now there have to be certain criteria or parameters determining which determine what is the optimal path, right? If on Google Maps you're searching which is the optimal path is generally the one which has the least traffic, right? If you can go from place A to place B via two different routes, Google Map will always suggest you to go through a route where there is less traffic, right? That is the benchmark for Google Map, all right? So there are certain benchmarks based on which different Lightning Network implementations will suggest you which route you should take to transfer the payment from person A to person B. All right. Now there need to be certain benchmarks for that. All right. So basically LDK, which is another implementation of the Lightning Network, has set up a mechanism which gives scores, right? Which gives scores to channels, which might even give scores to channel participants. All right. And this is done using probes. Like you can later on look at what probes are. Basically, it's like sending dummy payments through Lightning channels, which are destined to fail. And through these probes, you can query a lot of things about channels like the channel liquidity, etc., etc. All right. So you can do probes to analyze which channel has more liquidity, which channel is transferring payments quickly, for which channel the failure rate is less. Based on that, you can give scores to channels and participants to the Lightning Network. All right. And when you have scores and you have multiple options to which you can route the payment, you look at which channel has the highest score and you use that channel to route your payment. So this mechanism has been incorporated in LDK, which already existed, I believe, in other implementations like LND. Right. So we covered LDK, a couple of LDK PRs, I believe. We covered an LND PR, we covered a Bitcoin Core PR, and we covered a vulnerability related to one of the versions of LND. This is what we were able to cover in 1 hour. I don't think we'll be able to extend it any further. So I'll stop sharing my screen. And if there are any questions, any thoughts, any closing comments, then please feel free to go ahead and ask questions or share your thoughts. Coding P is typing something, so I'll wait for her to finish. OXFA is also typing something. Hey, you're most welcome, OXFA. Thanks a lot for showing up.